minus rate out. Now, what is this going to be measured in? dx dt. What are the units of that going to be? Rate of change of pounds, right? Amount of salt in pounds with respect to time. So I'm just going to write this as pounds per minute. Okay, so that's what we're looking at. How do I figure out what's the rate of salt going in?
0.
Oh, 0, right. 5 gallons, what's the rate of water flowing into it? 5 gallons per second?
They're all 5 gallons per minute, it looks like.
5 gallons per minute.
Oh wait, 38, good God, I looked at 37, I saw 5 gallons per second. I was like, oh, we have to convert stuff now? No, okay. 5 gallons per minute. So the rate that water's going in, well, we got 5 gallons per minute. I'm gonna write the units out. 5 gallons per minute, but what's the concentration of salt in that? 0. And this is 0 pounds per gallon. So I'm writing all the units in here very carefully because I want to make sure everything comes out. This is 0 pounds per gallon. That's what's called the concentration. Okay. Now minus the rate out. The rate out is going, well, water's flowing out, or solution is going out of that tank again at 5 gallons per minute. But what is the concentration?
X sub t over 100?
Right. There, the solution, or the concentration of the water, the solution going out, there is X of t at any time, X pounds of salt dissolved in 100 pounds of solution. So this is X over 100, and this is X is pounds, and 100 is gallons, right? So X pounds per 100 gallons. Oops. And I wanted to show this why, these units. Right, so we got a concentration of fluid going in. We've got a concentration leaving, and that's variable. All right, and also to show you that what cancels, gallons, so we'll end up with pounds per minute, gallons, pounds per minute. So we got dx dt equals, that's just a big 0 on the left. So salt is leaving at negative 5x over 100. All right, so negative 5x over 100, which, we could simplify to negative x over 20. Okay. And yeah, it would be pounds per minute. But it's a variable concentration going out because we're assuming that it's thoroughly mixed, so it's more and more weak as time goes on.
X is less than or equal to 50 with that.
We know we have an initial condition that at time 0, what is it? At time 0, X represents the amount of salt. At time 0, there is how much in tank 1? 50 pounds of salt. So here we go. We got our differential equation. This one might be separable all around. Okay, but to show that it can be handled another way.
I think it is separable because we did these in Calc 3 as separable equations.
Yeah, it is separable. And I think it might be easier to do that, but I want to do it using integrating factor and show that it can handle that. So an integrating factor can handle a larger class of differential equations. So we have dx dt, and if I write that on the other side, I have plus, I'm going to write this as 1/20th x. We've got to be careful because x is our dependent variable here. Okay, before it was our independent variable, and the right side of this equals 0. So our integrating factor because I just added x over 20 to both sides and got it over to the left. So I cleared the entire right side.
So that becomes your Q. So X is the constant 0.
This is our p, and I'm going to call it p of t because our independent variable is t. This is linear in x. And that's the dependent variable here. And it can be confusing when the book switches over to calling x a dependent variable. And here time is the independent variable. Okay, so our integrating factor, that's our p of t, that's our q of t. Okay? So our integrating factor will be what? Right, and this is rho of t. It's going to be e to the integral p of t, and that's 1/20th. Okay, and what's integral of 1/20th dt? Just t over 20, linear. Plus some constant. Oh, I don't need the constant up there. Okay. And then, just like we did with the other ones, we take that integrating factor and multiply both sides of our equation. Okay? So e to the t over 20 dx dt plus, and I'm going to put that, I'm going to slide in the e to the t over 20 after the 1/20th because then it's more recognizable as a derivative, isn't that? 1/20th e to the t over 20 times, and what we got is x, equals, and if I multiply it on the right side, I still get 0. Right? So that integrating factor just makes it so that the left side is derivative of a recognizable function. And this is the product rule, e to the t over 20 times y. Oh, sorry, x, because x is our dependent variable. So this is derivative with respect to t of e to the t over 20 times x. Right? If you follow the product rule and know that x is a function of t, that's what you get. So now we integrate both sides. Well, yeah, this side just gives me, I'm going to write it as x e to the t over 20 equals, and what do I get when I integrate this? Yeah. Well, 0. What kind of functions have a derivative of 0? Constant. Right, so this is our constant right there. And finally, dividing both sides by e to the t over 20, c over e to the t over 20, or alternately, might like to write it like this using a negative exponent, e to the negative t over 20. Okay, so how do I recover this initial condition now? Or the constant? Yeah, yeah. We got that initial condition. At time 0, remember x is the dependent variable. It's the amount of salt in this case. So x of 0 gives me 50 pounds. So when we put in 0 for t, we get what? C e to the 0 equals 50. So we get c equals 50. E to the negative t over 20. All right, and that's what we were after, the amount of salt at time t. All right, part A. Tank 1 at time t. And t was hours. Wait, what was it? Yeah. Oh, no, minutes. Everything was in minutes. Minutes.
to like the A times E to the KT, would that be like,
Oh, right.
because that was pretty much exactly like that.
Yeah,
so-
yeah. Yeah, and it'd be interesting because it was separable. If you solved it that way, then you should come up with the same thing. What happens is, as time goes on, so imagine t going to infinity. What happens?
Decrease.
As t goes to infinity, it's a negative exponent. So that becomes closer and closer to 0. Okay? If you thought of it down in the denominator, 50s, and our constant was 50, e to the t over 20, as t goes to infinity, that denominator becomes larger and larger and larger, and this goes to 0. Okay? So what that says is eventually what's happening to the salt?
Slowly but surely going to 0.
Mm-hmm.
But it never leaves.
Mm-hmm. Yeah, it would never be all the way gone. It's always mixing up and flowing ever weaker, the solution, the concentration. Yeah.
Miracle of perfect homogenization.
Instantaneous homogenization. So you imagine that if you took a thimbleful of fluid, it would have the same concentration as everywhere else. Yeah, that's a big assumption.
So, when we're doing this, can we get the integrating factor and skip the multiplying step and just assume that we're gonna get a product rule?
Right. But unless you can recognize right off the bat that you have the left side the way you want it, like Hannah asked.
But it's always the integrating factor times the function we're trying to find.
Oh, right. Yes.
It's always the same.
So yes, you do need to find the integrating factor, but then imagine that it's multiplied because you'll always get the derivative of that on the left side. I see what you're saying. Yeah. Okay. Let's look at part B. Jeez. Part B says, suppose that y of t represents the amount of salt in tank 2. So this is the cascading effect. It's receiving solution from tank 1, which has brine mixed in. It's a variable amount input. And it's also flowing out, mixing up instantaneously and flowing out. Suppose that y of t is the amount of salt in tank 2. First, show that it satisfies, dy dt satisfies that equation. Okay? So they give it to you, but at least they say show that that's true. So in part B, let's let y of t represent salt and its amount in tank 2 at time t. All right. So then dy dt is equal to, I always write this step, rate in minus rate out. That gives us the right sign, S-I-G-N, okay, of our derivative. Okay. Now the rate in, well, that's coming from tank 1, right? So at any time in tank 1, there's x of t gallons, or sorry, not gallons, but pounds of salt mixed up in 100 gallons of solution. There's always 100 gallons of solution in it, but there's a variable amount of salt. So the rate in, how do I think about that? Well, right. It's still coming in at 5 gallons per minute, right? But the concentration is variable. We have X pounds of salt over at 100 gallons of solution. So this is X pounds of salt, 100 gallons of solution, right? That's the rate in, minus the rate out. Again, it's leaving at 5 gallons per minute. And the solution, when it leaves, well, there's an amount of salt, y of t, that represents the pounds of salt, mixed in with how much solution is there always in tank 2?
200 gallons.
It says that there's 200 gallons. It's twice as big. And that's measured in, again, Y is pounds of salt, 200 gallons of solution. So just doing a quick unit analysis, the gallons cancel out, gallons with gallons. We get pounds per minute minus pounds per minute. So that will be our overall net rate. So we get, I could write this as 5x over 100 minus 5y over 200, and I think that's the one that they asked us to verify. They said verify that it's, yeah, 5x over 100 minus 5y over 200. Okay, so now what do I want to do with that?
Solve for y.
And I do know, at this point, x is a function of t as well. We know that, though. We know that the expression for x is t. Okay? Okay, so I'm going to simplify this a little bit. We got dy dt equals, and x over 25 over 100 give me x over 20 minus, and the 5 goes into 240 times, y over 40. Okay, and in this case, y is our dependent variable, so that's good. The way we want to write this to recognize it as a linear, and by the way, this one won't be separable anymore, will it?
Oh, yeah, because there's no dx now.
Oh, right. Yeah, and x and y are both functions of t, but it's a minus in between them. These are not factorable in any sort of way where it's an expression involving x times an expression involving y. So this one, part B, not separable. Can't get away with doing it that way. But what I'm going to write is, I'm going to pull this over here, plus 1/40th y equals x over 20, right? Now, x is a function of t. We already know that. So we get dy dt plus 1/40th y equals, and what was x of t? 50 e to the negative t over 20. Okay, good. Another step. We got dy dt plus 1/40th y equals, well, shoot, that's just 5 halves. Didn't have to do a whole new line for this. 5 halves e to the negative t over 20. Okay. Now, again, this is good. Y is our dependent variable. That feels a little bit more natural to me. Okay. T is our independent variable. So this would be my P of t. And this guy is what we call the Q of t. Okay, in linear form. Okay. Linear first order. And it's linear in y. All right, so what would be our, what's our integrating factor?
E to the integral of 1 over 40.
Right, and I'm going to call it rho. You got to be careful so it doesn't look just like p, but rho of t is going to be e to the integral 1 over 40 dt. Right, and again, that's a constant, so it's not so bad. We just get a linear. It's going to be e to the t over 40. Okay, and multiply both sides of it. This is the part where, yeah, if you multiply both sides of it, then hopefully you should recognize that as the derivative. And what's it going to be the derivative of? Let's do this. It's derivative with respect to t of
e to the t over 40
e to the t over 40 times y of t. And on the right side, we got 5 halves e to the negative t over 20. Okay? All right, so yeah, and if you need that step, multiply both sides of the equation by that, and you can recognize that. That looks like a product rule. Yeah.
Do we also multiply the other side?
Oh, yeah. Times e e to the t over 40. Of course, it did. Yeah, that might help your mind to do it to both sides. So that's our integrating factor. A good thing is we can combine those powers of e. So, integrating this side we're going to have e to the t over 40 times y equals 5/2. And what do we get when we, these are powers of e. You need a common denominator though. This would be negative 2t over 40 plus t over 40. Add the powers of the same base. What do we get? Negative 2t over 40 plus 2 over negative t over 40. Okay. Oh, we have not integrated yet. The left side we did, but this side we didn't. So what's this going to give us? We got e to the t over 40 times y equals, I'm going to pull that 5/2 out of the integral. Pull that 5/2 out. What do you get when you integrate e to the negative t over 40? This is tricky because you're not using the product or the chain rule. You're using the chain rule in reverse.
So we don't have a t factor. Oh wait, that's useless.
Negative 40. Yeah.
I know I'm going to get an e to the negative t over 40. I always work backwards when I do this. If I differentiate this, that negative 1 over 40th is going to pop out and it needs to cancel with something. It's going to need to be what?
Negative 40.
Negative 40. So the negative 140 knocks it out and I just get e to the negative t over 40. Okay, plus some constant. Clean this up a little bit. The negative 40 over 2, that's going to be negative 20 times 5. Before I get this on the other side, that's going to be negative 100 plus c. No, negative 100 e to the negative t over 40 plus c. And then we could imagine multiplying both sides of the entire equation by e to the negative t over 40, or equivalently dividing by e to the t over 40. Okay, keeping track of these exponents is a full-time job. Okay, so we're going to have y equals, I'm going to have negative 100 e to the negative t over 40 times e to the t over 40, is that right? Oh, e to the negative t over 40, another one. Because I'm just multiplying both sides by e to the negative t over 40 to cancel that. Okay, so what do we get finally? I'm going to write this the other way around. I don't like to have minuses leading my expressions. Just type A, I'm weird like that. Negative t over 40 minus 100, and what do I get when I combine these powers of e? Negative t over 40, negative t over 40, I'm going to get negative 2t over 40, so that's negative t over 20 again.
It came back.
So it came back, that t over 20 came back. So this is the general form. Now, to recover that value of c, we need to use the initial condition. We know that at time 0, y of 0 represents the amount of salt in tank 2. We knew that was also 50. So there's 50 pounds of salt in each. So putting that initial condition, 0 for t, that's the good thing. E to the 0, that's just 1. E to the 0 is 1. So I get c minus 100 on this side, which we know to be 50. So what do we get for c?
Or 150.
So c is 150, I put that back there. 150 e to the negative t over 40 minus 100 e to the negative t over 20. I wish I could get those powers of e together, but they have different, these e's have different exponents. If they were both negative t over 40, I could factor them, but can't get them together. Okay, so that's our guy. Should we do part C? I don't know.
5 the maximum.
I think we should take a break. It's what, 3, we get done at 3:50.
Way past.
We're gonna take a, well, let's take a break now. We're gonna skip C. I'll have you guys do C on your own at home. It says at any time. What's the
We don't turn in homework.
Problem set?
Problem set? That's due Thursday.
Do Thursday?
So that's a California application. Did you get one of that
Yeah, because he was just going over some of the stuff today, or some questions over it. And you can turn it in still, I think.
Ah,
But,
just wait.
you know, but I think they'll take it. But